phosphate on it yet, plus an inorganic phosphate, a phosphate that's just kind of floating around inside the cytosol, and it sticks those two things together. It creates that last really high energy bond. So that's going to make ATP.
Is ADP plus what?
That's a P, a phosphate, with a subscript I.
ADP is percentage of ATP changes without that.
Right, so if I was to kind of diagram that, this would be our adenosine plus ribose. So I'm just going to put A plus R. And it's attached to two phosphates. And then we're going to add to that another phosphate. So that at the end, we have our adenosine plus our ribose, and 1, 2, 3 phosphates.
Negative?
Yep, they're all negative.
Is that everything?
This is everything for the first part of the light reactions.
I'm going to take a picture.
Yeah, for sure.
This whole thing is called the photosystem 2.
This is all associated with photosystem 2. Photosystem 2 is actually just that first rectangle right here. But this is the electron transport chain associated with photosystem 2, and ATP synthase is also associated with photosystem 2.
And this is the light dependent.
Mm-hmm. Okay. So we've created 50% of the stuff that we actually need to reduce carbon dioxide into sugar. We've created energy, right? That's all ATP is. It's just chemical energy. And that chemical energy is stored in that terminal bond between those last two phosphates. A really high energy, very unstable bond. Okay. So downstream from this, there is another photosystem, and it's called photosystem 1. And it looks nearly identical to photosystem 2. And I think that I have in Canvas posted this diagram, a PDF version of it, I think. Okay, so there are chlorophyll molecules in this protein matrix, a large chlorophyll complex in the reaction center core, and then also a primary electron acceptor up here. So this is PEA. Here, instead of being P680, it's P700. But the exact same things are going to happen. We're going to get some excitation by a photon. And excitation again means what? An electron on the magnesium ion bounces out an energy shell, right? It absorbs that energy and it increases its distance between that electron and the nucleus. When it falls back to ground state, that energy is released and passed ultimately over here to P700. And when P700 picks up that energy, it loses an electron up to the primary electron acceptor. Like so. P700 just got oxidized or reduced?
Oxidized.
Oxidized, exactly right. Now when P680 was oxidized, What reduced P680?
The hydrogen.
That's right, the hydrogens from the water, right? They lost their electrons. But that's not what happens here with P700. It doesn't happen because there's already an electron floating around somewhere. And where is that electron floating around?
The PE, the electron acceptor.
From right here.
Oh.
The electron that fell out of the electron transport chain. This electron actually comes over here, and it reduces P700. So we don't need to split any more water. On the exam, a question that I really like to ask is, which of the following molecules reduces P680? And which of the following molecules reduces P700? Where did that electron come from that reduced P700?
The PS1.
From P680. Yeah, it came from P680. Exactly right. Do you guys see that? This electron source is right here. It just followed this path to get to P700. Okay. You all right with that idea? So there's going to be another electron transport chain, and then there's going to be a large enzyme complex right here that's called NADP plus reductase.
Ooh.
Oh, and I should draw and connecting these as well.
Did you say NADP plus 1 reductase?
NADP plus reductase.
Okay.
And that plus will make more sense here in just a second. So same thing's going to happen, right? We're going to have this electron that leaves our primary electron acceptor and then falls down our electron transport chain. And then it eventually falls out. Same thing, you're going to get H pluses over here. And these H pluses are going to be pumped to this side of the membrane. Okay.
Where did those protons come from? Is it,
Wonderful question. Where could those protons have come from?
is it from when the ATP synthase popping back in?
Yep. And ultimately, their source is all this water split that's going on over here, right? This looks like a really crazy football play, right?
Yeah, it does. Did you just say the protons come from the
The protons come from ATP synthase over here, those that are falling back through. Okay, so these protons have a couple of destinies, but I'm only going to diagram one of them. Some of them are cycled back through ATP synthase to create more ATP. But I'm going to diagram the other thing. So really what we want to do is we want to make an electron carrier. And that electron carrier is called NADPH. And that's what this big enzyme complex does. what it does is it takes NADP plus and it sticks onto it an electron and a proton. That's a reduction reaction, right? Because it's actually picking up an electron. So here what's going to happen is we're going to take NADP plus an electron and a proton. I have to draw that correctly. And we're going to make, trying to hold too much stuff. And we're going to make NADPH. So question, where is this electron going to come from? Right here, right? So the electron that fell out of the electron transport chain. And these protons are going to come partially from the protons that are pumped across the membrane. So some of these protons are going to come back here and be stuck onto NADP plus. Okay. So question, why do we take NADP plus and reduce it and call it NADPH? Because of the proton and what else? The electron. And a proton and an electron is what kind of an atom?
A hydrogen.
A hydrogen. So we've essentially just stuck a hydrogen on to that molecule. The other question is, why do we even care about electron carriers? So that's my question to you. Why do we care about electron carriers? What is it going to do? In the form of, yeah, sugar. But how do we get sugar?
Through the chloroplast, or not
Chloroplasts are definitely
Sorry.
doing it. So we're going to take, remember, we're going to take 6 carbon dioxides and 6 water molecules, and we're going to convert that into 6 oxygen molecules plus a really large C6H12O6, right? And what we said was, basically what happens is this gets oxidized into that, right? Isn't that what happened right here? We took water and we oxidized it into oxygen gas. And then we're going to take this and we have a reduction reaction into that. What does reduction reaction mean? You're picking up electrons. And what's the source of those electrons? Where do we get the electrons? From NADPH. Basically, guys, what's happening is NADPH is shuttling electrons from this stuff and dropping them off on carbon dioxide. And it's taking all those electrons to build carbon dioxide up into sugar, C6H12O6. Now that is inherently an endergonic reaction, right? That's anabolic. We're taking something small and we're making something big from it. And what we know about endergonic reactions is what? They require energy or they release energy. It's the opposite of release. They require a bunch of energy, right? Because we're building something big, and so they're requiring a bunch of energy. And where do we get that energy from?
ATP.
ATP right here. So you guys, the light reactions have 2 purposes: to make energy and to make electrons. And we're going to use that energy to reduce carbon dioxide into sugar. The purpose of the light reactions is to make all of the stuff necessary to make sugar. We're not making sugar at this point. We're just making all the stuff to make sugar, okay? So, question. Which molecule is the source of the electron that reduces NADP+.
Wait, can you repeat that?
You betcha. What molecule is the source of the electron that reduces NADP+.
P680.
What were you saying, Adam? P700.
Oh.
P700 loses an electron before it picks one up from P680, right? Because it has to be oxidized before it can be reduced. And that electron comes over here and it reduces NADP+. So, which molecule reduces P680?
P4.
Which one reduces P680? Water. And what reduces P700?
P6.
P680. And what reduces NADP+? P700.
Oh, so good.
Okay, can you go through that one more
You
time?
betcha.
Just that one little bit you did right
You betcha. So the question is, what reduces P680? What
That's the
molecule
water,
is the source
right?
of the electron? Yep, water.
Okay,
And what reduces P700? The electron that comes from P680.
okay,
And then what reduces NADP+?
P700.
Yeah, the electron that comes from P700.
I got it, it's just a lot.
So, we'll go over this again at the beginning of Wednesday. But for now, what questions do y'all have about the light reactions? The dark reactions are inherently simpler than the light reactions.
So with this electron happening at P70, so another.
This right here?
Yeah, so you have to have another proton, or a photon, I mean, to come in, and that is what, is that reducing P70 to take that electron?
Adding them all together to get.
Exactly right. So we have excitation, and that excitation energy is passed to P700. And when that energy is passed to P700, it loses an electron.
But then that other electron comes in from the other chain and oxidizes it? Okay.
It reduces it.